Hey there, class. We're here today. We're going to look at an example, and this particular example is example 1. Now, this was an example that we had actually solved previously. This particular example was an example that we had solved using more of a kinematics approach to this, and certainly if you want to watch that video looking at this from a kinematics approach, I'll put a link in there for you so that you can actually watch it there. What I'd like to do today is kind of take a different approach at this. And in this case, the particular approach I'd like to take is more of an energy approach, looking at this from the standpoint of energy. So let's do that. Let's take a look at our initial snapshot here. And when we take a look at this object, I believe it was the wheel of this airplane. And we'll consider our system to be the wheel and the Earth. So we're going to have two types of energy. There's potential energy and kinetic energy. Since the object, in this case the wheel, is moving, it will in fact have kinetic energy. And because it's raised above the ground, it is going to have potential energy. So that's going to be mgh. So the total energy at this position is going to be the potential energy plus the kinetic energy. Let's go down here to the bottom where the object has gotten to the ground. Basically at this location, since our final height is 0, the whole of potential energy is gone. There is no potential energy at this point in time. The kinetic energy, on the other hand, is certainly not 0. It's at the instant it's just hitting the ground, and so this would be 1/2 times our mass times velocity squared. Now, something to note, one thing you want to watch out for here, different from kinematics, energy doesn't take into consideration any kind of direction here. This velocity that we're going to be solving for is the resultant velocity of both the x and the y component. So you do need to make sure that you are aware of that when you're looking at this. So let's come up with a strategy and let's see if we can implement that. Okay, so here is my strategy, and ultimately this strategy is going to help us find part B of this problem. In the end, we're going to actually use kinematics to find part A anyway, but for part B, we can use the idea of energy conservation. Since we assume there's no air resistance, and the only force acting on this thing is the force of gravity, we have what we call a conservative system. And so we can use the idea of energy conservation to find the velocity. And again, I want to make note here that this is going to be the magnitude only. Okay, this is not going to help us find the direction. So to find direction, we will know the resultant velocity. We will also know the original velocity in the x direction is also going to be the final velocity in the x direction because there's no acceleration there in the x direction, mind you. And so we're going to be able to find an angle that way. So to actually put this into practice, to implement, basically, once again, my original energy is both potential energy and kinetic energy. My final energy is just the kinetic energy. As we zoom in here, you'll notice that the m's are going to cancel out. It kind of divides out here, and that lets me with what you see here. My goal here is to get the VF by itself, so I'm going to multiply both sides by 2. That's going to get rid of this 1/2, and it'll put the 2 out here, and then I will take the square root of everything, and that's where my square root comes in. When I substitute my numbers in, I end up with 220.7 meters per second. Now, the next part was to find the angle. Keep in mind this is an angle below the horizon. Okay, if you remember, our velocity looked something like this. Okay, this was our velocity, and we have an x component. Oh, sorry, that's the y component, and we have. So this is our vx, and this is our vy. And the angle we're looking for is right in here. Okay, that's the angle we're looking for. So if the cosine is going to use the final velocity and the x component, and that x component was the 138.9. So basically, I end up solving for the angle of about 51 degrees. So to put this as a final answer, or as final response, to find the final velocity, it's going to be 220.7 meters per second at 51.0 degrees below the horizon. And once again, as far as part A goes, you're going to need to use kinematics on this. So honestly, you can watch the other video on this one to see how that would be done.